Hello students, in this video we'll discuss the Maxwell equations from electromagnetism in connection with the wave equation. So let's consider the Maxwell equations from electromagnetism. If we want to consider these equations, we have an electric field. We have an electric field E, it's a vector field. X, Y, Z, T is an electric field. We have a corresponding magnetic field. Like that, the magnetic field. And we get a couple equations, a couple of vector equations for these things, right? The first of the Maxwell equations is the Maxwell Ampere equation. This is also Ampere. And what does this one say? It says the time derivative of the electric field, is the speed of light times the curl of the magnetic field, and then minus 4 pi J, and that J is the current density. Okay, great. Then it says the time derivative of the magnetic field, is equal to what? Is equal to negative C, the curl of the electric field. Of course, there's a sign convention with this. And then what? And then number 3, so this is 2. Okay, and this of course is Faraday's law. Okay, and then the next 2 are divergence conditions. 3 is that the divergence of the electric field is 4 pi times rho, which is the charge density. Okay, and finally the fourth one over here, the fourth equation is that the divergence of the magnetic field is equal to 0. Those are the Maxwell equations. Okay, we're going to work on some special cases in order to make it clear how it connects to the wave equation. We're going to work on the special homogeneous case, when the charge density and the current density are 0. Homogeneous case. We're going to set what? We're going to set the J to be equal to the 0 vector and the charge density to be 0. Okay, that makes the equations homogeneous. And so now what we're going to do is we're going to try to connect these to the wave equation by taking another derivative. So take d by dt of 1 and 2. Okay, and so what we get if we do that, okay, we're going to get the following. We will have ETT, so I'll have the second t derivative of the electric field is going to be C times the curl of the t derivative of B by passing the t derivative inside the curl, which we can do. We can just swap the partial derivative order, right? There's no current density any longer, so that's gone. And now I can feed in Faraday's law into this. And so this says this is going to be C curl of what? Curl of the negative C curl of E. Okay? Now, of course, this just becomes what? This becomes negative C squared, and then the curl of the electric field E. And so now let's recall from vector calculus. We've proved this in a previous video, so recall that if I do the curl of a vector field, what is this? The curl of the curl is the gradient of the divergence of the vector field minus the Laplacian of the vector field. We proved this in a previous video. Okay. And so now, of course, what's going to happen over here? So for our problem over here, so if I recall this fact over here, we can keep going with our calculation. Our calculation now becomes what? This becomes negative C squared. And I'm going to have the gradient of the divergence of E minus the Laplacian of E. Okay, there's no divergence of E, so this just becomes what? This becomes C squared Laplacian of E. Okay, so what we just shown, so hence we know that ETT is equal to C squared Laplacian of E, and this is the 3D wave equation. Great, okay. We can do the same thing with the B equation over here. So I can do B TT is going to be what? It's going to be, well, BTT is going to be negative C gradient cross E, so curl of ET, right? And this is negative C curl of ET is going to be the C curl of B over here. And again, by exactly the same reason, since B has zero divergence, this becomes what? This becomes C squared Laplacian of B. And so that says that B satisfies the 3D wave. B satisfies the 3D wave. Nice, okay? And so now, of course, I've just shown that both the magnetic field and the electric field satisfy the wave equation, right? And so now we can apply Kirchoff's laws, right? So for a fixed t, so given a fixed what? A fixed point x0, t0, we can use Kirchoff to find that, for example, the electric field at a given point, and of course that's a vector x naught, t naught, is really going to be what? Is really going to be 1 over 4 pi t naught, the surface integral over the light cone, x minus x naught equals c t naught. And then I'm going to have the curl of the initial magnetic field. So curl of the initial magnetic field, s d sigma s, plus the time derivative, 1 over 4 pi t naught. And then we're going to do the integral of the light cone. Again, x minus x0 is equal to c t0, right? And then this time we're going to have the initial electric field, right? The initial electric field, s d sigma s, like that, okay? Those are the initial electric fields, right? And so of course, this set over here, x minus x0 equals ct0 is the light cone, at x0, t0. In other words, the electric field is going to be, what are the values of the electric field are completely contained based on the initial conditions off of the light cone, right? And so that gives a good intuition for how the connection between the light cone dynamics and the dynamics of the electric field and the magnetic field work, because they're solutions to the three-dimensional wave equation, right? So that's a beautiful connection, taking one derivative and using vector calculus identities to prove really, really interesting results about the electric field and the magnetic field of a system. Thank you very much.